This video we talk about a shift register. Shift registers are typically made out of edge trigger D flip-flops, and the example that we're going to look at in this video uses negative edge triggered D flip-flops. So I've repeated the truth table for negative edge triggered D flip-flop right here. So we talked about this in a previous video, and remember that the operation of this type of flip-flop can be summed up that the output Q will equal the input D only at the time of the 1 to 0 clock transition. Okay, for all other time, the outputs are going to remain the same no matter what the D input is doing. So again, this type of flip-flop stores data at all time except for this negative edge. The only possible time Q can change or the outputs can change is at the time of this 1 to 0 transition on the clock input. So here's a diagram of a shift register. This is a 4-bit shift register. Notice that it's synchronized because the clock inputs are all connected together. And notice that the Q output of one flip-flop connects to the D input of the next. So this is a similar type of connection as to how the counters were connected with JKs. Anytime you have the output of a flip-flop going to the input of another flip-flop, it's called a Cascade Connection. So the counters we looked at were JKs cascaded together that were synchronized, and this register here, this shift register here, is cascaded and also synchronized since the clock inputs are connected together. So notice that this input over here is labeled the serial input, and this output over here is labeled the serial output. We'll talk about why they're called those names coming up. Okay, so what we're going to do to see how this shift register works is we're going to do what's called load a shift register. And loading a shift register just means that you put data into the register. So in this example, we're going to load a binary 0, 1, 1, 0. Okay, so if this was binary code, this would be a binary 6. Okay, so for whatever reason, we want to load this data into the shift register. So initially, all the outputs in our clock and our serial input are just don't cares. Okay, that's what these dashes mean, that these outputs and inputs are equal to 1 or zeros, but initially we just don't care what they are. Now, in order to load the 0, 1, 1, 0 data, the first thing we need to do is make the serial input 0. Okay, make that a low. And then once we make the serial input a low, we're going to clock the register. So we're going to provide a 1 to 0 transition on the clock input, and that 1 to 0 transition is on the clock input of all the flip-flops that make up the register. And at the time of that transition, okay, going back to our diagram, at the time of that transition, the Q output of each edge trigger D is going to equal its input. So you see Q3 is going to equal its input, which is connected to output Q2. Q2 is going to equal its D input that's connected to Q1. Q1 is going to equal its input, D input, which is connected to Q0, and Q0 will equal the data that's on the serial input. So what happens is that all the data gets shifted one place. That you see at the time of this transition, Q3 is going to equal Q2, so this don't care that was at the output of Q2 is now at the output of Q3. Q2 is going to equal Q1. Q1 is going to equal Q0. And then Q0 is going to equal the serial input data. So you see all these don't care shift over one place, and then the serial input data comes into Q0. Okay, well, continuing on here, the next thing we need to do is make the serial input equal to a 1, and then clock the register a second time. And these bits are going to shift one place over again. Okay, because Q3 is going to equal Q2 again. So this don't care is now at Q3. Q2 is going to equal Q1. So now that don't care is Q2. Q1 is going to equal Q0. So this 0 is now at the output of Q1. and then the serial input data equals Q0. It comes into the register. Okay, so this is why this device is called a shift register, because for every clock pulse, the bits at the output of the register are all going to shift one place. Okay, so to finish this off, we need a 1 here, clock it a third time. Okay, and after that third clock pulse, this is what we'll have inside our register. Okay, and then make the serial input a 0 and clock a fourth time, and after that fourth clock pulse, okay, we have the data loaded. Now I'm putting this rectangle along with these squares around each of the bits just to let you know that a lot of times this circuitry over here that depicts the register, the shorthand notation is this: the rectangle represents the register and each square represents a flip-flop that holds a bit at its output. So this would just be shorthand for this whole diagram once the register is loaded. Okay, once the shift register has been loaded after the 4 clock pulses. Now you can have shift registers that hold more bits, just like you can have counters that have more bits, and just like with the counters with registers, each flip-flop holds a bit. So an 8-bit shift register would have 8 flip-flops, just like a counter that has 8 bits would have 8 flip-flops, right? There's a flip-flop per bit. Alright, well, the last thing in this video is that just by simply loading a shift register like this, we perform a very useful function. Because you see, what we've done here by loading the shift register is we have done a serial, or we've accomplished a serial to parallel data conversion. Okay, because the input on our serial input is data that's displaced in time. Okay, because on one wire we had a signal that was equal to a 0, then we clocked it, we made it a 1, we clocked it a second time, we kept it a 1, we clocked it a third time, made it a 0, clocked it a fourth time. So you see the serial input has data that's displaced in time. Well, once the shift register is loaded, okay, after the 4 clock pulses, that same data is now displaced in position, and each bit is on its own piece of wire. So, you know, we had Q0, Q1, Q2, Q3, and we got 0, 1, 1, 0. So just by loading a shift register, you're going from serial data, which is data displaced in time, to parallel data, which is data displaced in position, where the bits have their own wire. Serial, there's just one wire for all the multiple bits because they're displaced in time. And this is a very useful type of data conversion that's done in computer modems. You know, the reason you need this type of conversion is when computers talk to each other, when there's transmission between computers, especially over long distances, it's done in a serial type format. But computers process in parallel because they can process much faster in a parallel fashion. So this would be one end of a computer modem. The other end of a computer modem would go the other way. You'd go from parallel data to serial data, and that's what's accomplished when you unload a shift register, which we're going to do in the next video. But the last thing in this video, and this is really important, a really important definition, is that there's two types of shift registers. There's shift right Okay, shift right, shift register. So SR here stands for shift register. And there's also shift left. Okay, what's meant by a shift right, shift register is that the serial input data goes into the Q0 flip-flop. Or, excuse me, that's not correct. Sorry about that. That's a mistake on my part. If it's a shift right, shift register, the serial input data would go into the most significant bit flip-flop, no matter what it's called. Alright, and if it's a shift left, the serial input data goes into the least significant bit flip-flop. Okay, so in this diagram, if we made Q0, if we made this flip-flop the most significant bit, and it's the designer who decides which bit is most significant and which is least significant, you know, which flip-flop's holding the most significant bit and which flip-flop's holding the least significant bit. So if we say this flip-flop right here that's got the Q0 output, if this is our most significant bit, well then this would be a shift right shift register, right? Because see, the serial input is coming into the most significant bit. And what's really important to understand is that it doesn't matter the orientation of the diagram or the physical register for that matter, that once we label this Q0 flip-flop as the most significant bit flip-flop, and that's where our serial input is, that makes this a shift right shift register. So if, you know, this diagram were to be rotated, okay, we're now, you know, the diagram is vertical like this. Oops. Alright, as long as this flip-flop is our most significant flip-flop where the serial input is, this is still shift right. You would not call this a shift down shift register, okay? It doesn't have anything to do with how the actual, or what direction the actual bits are shifting in. You know, here the bits would be shifting down as we clocked it. But again, the orientation doesn't matter. It's just that if the serial input is coming into the most significant bit of our register, then it's a shift right. Okay, so just to emphasize, you know, if I were to rotate this and make it like this, okay, where again, this is our most significant bit here, Q0, even though the data would be going right to left, it's still a shift right shift register. Okay, a shift left shift register is just when you make the flip-flop where the serial input is the least significant bit. So now if we were to change and say, okay, this flip-flop with output Q0, that's our least significant bit of our register where the serial input is, well now this is a shift left. Okay, and again, it doesn't matter how the circuitry is oriented. Alright, if this was our least significant bit, this would still be a shift left even though the bits would be going left to right. Okay, so that's a common error that's made, is people think that the shift right and shift left just depends on, you know, what way the bits are going, but that's not what determines it. Okay, it's the definition that we have here. You know, what I tell students is, you know, the way to remember this is just think that, well, the register could be drawn in a vertical fashion, and if it's a vertical fashion, you know, the bits would be going either up or down, but you don't call it a shift up or a shift down. Okay, it's just shift right is when the serial input data goes into the most significant bit flip-flop, and shift left is when the serial input data goes into the least significant bit flip-flop.